All right, this is our last topic of study in Unit 4, and it's a pretty meaty one. It's about as meaty as the motion one was. And it's not like the motion one, which had lots and lots of different pieces. It's more that this one is more, here's your word for the day, amorphous. It's harder to pin down. It's harder to be precise about. There's a lot more options in terms of exploring this and where it works. And we're going to start today by looking at some of the supporting skills. So these are necessary components to doing what is known as related rates, which is our investigation of change using calculus. And the first skill we're going to look at is this one. We are going to differentiate with respect to t these three formulas. So you can all see those formulas just fine, right? Yeah, we can see those just fine. And I'm going to ask you to differentiate all of those with respect to time. I will be pausing the recording here. Like I've said before, and will continue to say, you are the captain of your own ship of the line. I cannot force you to do these things. You have to choose to do them. Please trust that they're designed with the intent of you learning well in mind, and give them your full effort. So for number one, d/dt is 8 pi r dr dt. So there are a few things I'd like to do here. The first thing is d/dt, that is the change in area with respect to time, or the change in area over time. dr dt is the change in radius with respect to time, or the change in radius over time. R is the normal r, the radius. If you're curious about where the 8 came from, when I took the derivative of r squared, that's 2r. But since I'm taking the derivative of r with respect to time, r and t don't match. I need a dr dt like we practiced with implicit differentiation. The last thing I want to mention here before we take a look at 2 and then 3 is this is the reason why you may have noticed I never wrote y prime when I was taking the derivative implicitly. I'd always write dy dx. And that was to set you up for success with related rates, because if you just call it a prime and you don't remember I've taken the derivative with respect to time, which is the nice thing about writing dA/dt, it tells you you've taken the derivative with respect to time, that you may get into a little bit of trouble when you're doing these problems, because related rate problems are challenging and they require you to focus on the whole problem and to check your work constantly and go back to things and make sure you're being thorough. So here's the second one. Hope right now you are checking your work and not just copying down what I have, because one of those, the checking work, is much more active than the other one, copying. So again, we have dV/dt, the change in volume with respect to time, and dr dt, the change in radius with respect to time. It's 4 pi r squared because the derivative of r cubed is 3r squared, and 4/3 times 3 ends up being 4. Okay, let me go over the next one, which was number 3. So for number 3, took the derivative with respect to time. Notice how I used the chain rule. And something else you may have noticed is that for 2c dc dt, which you might have, I have 0 there. The reason why I have 0 there is because c is a constant. So if we were to take the derivative of a constant c, we get 0. If we're to take the derivative of a constant c squared, we still get 0. So think of it like 5 and 5 squared. might be a little bit more manageable for you to consider. 5 squared is 25, and we know the derivative of 25 is 0. So the derivative of 5 squared should also be 0. Just because it has an exponent or some other function in it doesn't change it from being a constant to being a non-constant. Similarly, if you're taking the derivative of sine of 2 is a constant, and that's going to be 0. So I did clean this up just a little bit, algebraically speaking. I multiplied the 1/2 by the -2, and I moved the negative exponent to the denominator. That is not necessary, but I think it is necessary for processing reasons because negative exponents tend to be confusing. So I'm going to give you 3 more to practice and 3 more minutes to try it in. I will be pausing the recording here. So, number 4. Number 4 ought to look like this. dv dt, the change in velocity with respect to time, equals pi r squared dh dt. So you may be wondering about why we don't have a dr dt this time. That's because we treat the pi r squared like we treat a constant. So we have pi r squared times the derivative of h. The derivative of h is 1, but we're taking the derivative with respect to time, so we have to multiply 1 by dh dt. Number 5, I did in a similar fashion. What I mean by that is I looked at the x over 15 not as a quotient, but as a 1/15 times x. When I looked at this as a 1/15 times x, I said I have the derivative of cosine, which is the opposite of sine, but I'm differentiating with respect to t. Since I'm differentiating with respect to t, the derivative of the inside function theta is 1 d theta dt. Just like if we had the derivative with respect to x of the cosine of x, so a completely different problem. So if we had d dx of, cosine of y, we would have the same thing here, but in the place of theta, we'd have y, and we'd have x instead of t. So the letters have changed. The ideas, the concepts, the procedures have not. This last one, my expectation was that you all did it wrong. So if you did it wrong, that's great. So while you're writing this down, I would just like you to think about, where did this come from? Because I'm pretty sure most of you are going to be writing that one down. So where this came from was pi r squared, 1/3 pi r squared times h. And because r squared and h are both variables, meaning neither one is a constant, meaning I can't do the same thing like I did in number 4, but have a 1/3 involved. Because r is not constant this time, we have to use the product rule. So the first thing was I took the derivative of r squared, and that's where the dr dt comes from. The derivative with respect to time of r squared is 2r dr dt. And the second time I took the derivative of h, which is where the dh dt comes from. So the volume of a cone, the change in volume of a cone, has the change in radius and the change in height. So there were a few questions I'm going to address. I just have to check on them. While I'm looking at those, I'm going to ask that you look at doing number 6 a second time. This time for number 6, I want you to do it as h is a constant. Thanks for trying number 6 a second time. We are going to take a look at that and then take a bit of a break here. So if we treat h as a constant, one way you could process this is to say you have the constant 1/3 pi h, that whole thing is a constant, times r squared. So when we differentiate with respect to time, v becomes 1 dv dt. And then I have 1/3 pi h times the derivative of r squared, which is 2r dr dt. And dr dt, again, is the derivative of r with respect to t, or the change in r over time. So that's one of the necessary supporting skills that we've previously studied that we're going to use a lot in related rates. We're going to talk about what some of those other skills are in just a little bit. Okay, so in the handout, we're not going to follow the directions because it's really not that interesting to talk about optimization versus related rates, mostly because you don't know anything about optimization. Instead, we're going to take a look at what it means to apply calculus in a context of change by checking out number 2. And by looking at these contexts, my hope is you'll understand why related rates is thought to be difficult, because it is, again, hard to pin down. No single problem is exactly the same. You can't get one recipe to say, do this, and then do this, and then do this. It doesn't work every time, and you can't memorize problem types, and you can't prepare for things in advance in that fashion. What I'm going to try to emphasize for you are general ideas that will be successful across the board when it comes to related rates, instead of trying to focus on doing this type of problem or this type of problem. And that's because, as you may have noticed in math now, in the land of calculus, that these types of details and attention to things that are significant matter only when they matter, which is, again, not helpful, because how do you know if it doesn't matter if you know it doesn't matter? You don't. So we plan for that in advance. Anyway, particle moves along the parabola y equals x squared with its x-coordinate increasing at a rate of 0.5 centimeters per second. At what rate is the particle's distance from the point 30 changing when the particle is at 2, 4? So we're not going to solve this all of the way. I'm just going to show you a couple of different ideas about what you could do here. So one of the essential skills with related rates we've already practiced. And that essential skill is taking the derivative of an equation with respect to time. So number 2 presents the equation y equals x squared. If you differentiate y equals x squared with respect to time, what are you going to have? You're going to have dy dt equals 2x times dx dt. That's what you're going to have. All right. So we have in this equation dy dt and dx dt, which I'm writing some pretty horrible abbreviations for. So dy dt is the change in y with respect to time. Dx dt is the change in x with respect to time. There's another equation that we could use here that might help. And the only way we know which equation to use comes down to actually sitting down and solving the problem. So here's something else that we might try. How about calculating the distance? How would you calculate the distance? While you're thinking about that, just kind of imagine that this is what we have going on. We have an XY axis. We have the point 3, 0. And we've got the parabola y equals x squared that looks like this. And what we're thinking about is, if we're at this point on the parabola, that is the distance that we're talking about, right? That point to the parabola, or that point to a point on the parabola. So this distance, that's when we're right there, okay? What if the point is at a different spot? What if the point is right here? The distance is like that, right? That's how you calculate the distance between those 2 points. All right. If we're at a different point, like say this one, we'd calculate the distance like that. Yeah. So this is kind of why we need calculus, because we have things changing here that are hard to keep track of. We can't just write a real easy equation with x in it and solve for x. We got things changing. That's why we're going to have stuff like dy dt and dx dt. So we're going to have vertical change and we're going to have horizontal change. So what I mean by that is taking a look at all those points that I plotted and the corresponding distance. Each one of these distances has a different horizontal change and a different vertical change, both between each other and among each other. Okay. So that's pretty complicated to think about. Here's something else that's complicated to think about. There's another equation or formula or model we could use here to represent what's going on. We could do this, maybe this is what works, with the distance formula. So do you remember how the distance formula works? Okay, the distance formula is the square root of the change in x plus the change in y. And that comes from using the idea of the Pythagorean theorem, where this distance represents the hypotenuse of the triangle. Those red things, those are all hypotenuses of triangles. And then I can draw a vertical distance and a horizontal distance that I could then calculate like so. So for this particular one, that's the vertical distance and that's the horizontal distance. And if I find those and square them and then take the square root, I get the diagonal distance. So it could very well be for this particular situation that we use the distance formula, which is not that. Now we would use a little different form of the distance formula here, of course. I'm just going to use capital D for distance. We'd probably do it like this. Right? Because we know that we're always going to be at the point 3, 0. So one of those x values is 3 and one of those y values is 0. So then we differentiate this with respect to time. That's going to be similar to the third example we looked at, okay? The third example we looked at has very similar results to this. So hopefully that communicates to you some of the ideas that you could have to draw upon to do a related rate question. We're not interested enough in that question to finish answering it though. We're going to instead draw our attention here to number 4. And we're going to kind of think the same thoughts. So number 4, we're pumping air into a sphere at a rate of 6 cubic centimeters per second. We're asked at what rate is the radius of the sphere increasing when the radius of the sphere is 8 centimeters. Now something that's interesting here between 4 versus 2, I mean, it's a completely different situation, right? We've gone from something that's in the XY plane to something that's a sphere. So imagine like a balloon, a perfectly spherical balloon instead of those oblong balloons that you're used to, okay? And we're pumping air in. Another thing that's really different here is there's no formula. There's no formula. This is pretty common in related rate situations. You're not given a formula or model or equation to work with. Part of the process, part of the challenge is coming up with that formula. So there are different ways you could do this. Fortunately, we recently reviewed a couple of relevant formulas. Oops, that shouldn't be V, sorry. That's the surface area. This other one is V. The wrong exponent, sorry about that. There we go. Okay, both of those talk about a sphere, right? How would you know which one makes sense? This was a question we didn't answer in the previous one, but we're going to answer here because we're trying to build on our understanding as we get a little bit more used to doing some of this. So which one would we use here? Well, it depends on reading and rereading and thinking about the context. If you're pumping air into a sphere at this rate in cubic centimeters per second, does that represent the change in surface area, or does that represent the change in volume, or does that represent the change in radius? And this is where the picturing or conceptualization process comes in. Sometimes that's literally drawing a picture. Other times it's thinking through what's presented and creating a mental picture of what's happening. Those are both valid forms of processing and picturing. So which one were you thinking about as I was doing all of that talking? Air is pumped into a sphere. Does that sound like that air going in, that is surface area that's going in, or does that sound like volume that's going in? That awfully sounds like volume to me because volume is the inside stuff and surface area is the outside edge or bit or piece, or to be a little bit gross, skin, right? Surface area is the skin. Okay. Here's another one that's a related rate. And from looking at these and me talking about them and you listening, we're going to next talk about the general or related rates principles. So here's the last one we're going to look at in this fashion. And again, we're not finishing these questions. The goal is not to finish them. The goal is to be exposed to them a little bit and just get our brain thinking about what's going on here, which I know is not enough to actually sit down and solve one of these on your own. I get it. So take a look at number 5. Water flows into a cylindrical tank with base radius 3 meters and height 12 meters at a rate of 3t squared minus 8t cubic meters per hour. At what rate is the height of the water changing when 2 hours have elapsed? Notice how my first comment for the previous one, number 4, is relevant here. No formula is given, is it? Nope. So we'd have to make sense of what's being given here to determine what a relevant formula is. And we talked about how air going into a sphere was volume, water going into a cylindrical tank is also going to be volume. So from the context here, we know that we ought to be looking at the volume for a cylindrical or a right cylinder. We assume this is a right cylinder rather than an oblique cylinder. And when we differentiate with respect to time, dv dt, that's not the problem. The problem is the pi r squared h, because that's a product. So I have the constant pi, and I take the derivative of h once. So it's pi r squared dh dt. And then I take the derivative of r squared. And the order here doesn't matter a whole lot. I usually just find it easier to have the differential piece, the dh dt, the dr dt, as the last part of it. That makes it easier for me to read through and process. I think you'll probably feel the same way. So if we actually wanted to solve this, it says, at what rate is the height of the water changing? Where is that in the formula? That's right here. dh dt is the rate of change of the height of the water in the cylindrical tank. So that's what we'd be solving for. So there's one thing we know from all of our years of math experience. That means if I'm solving for dh dt, I have to know dv dt. I have to know r, I have to know h, and I have to know dr dt. Otherwise, I'm gonna have a really hard time solving this equation for dh dt if I've got one equation with multiple variables in it. I need more than one equation. I need additional information. So here are the general principles of looking at related rates. The first one, I can't model for you well without being extremely tedious. You're going to need to pretend that a related rates question is like a question in English class. You are going to have to read it and reread it and write a formula and go back and write another formula and go back and differentiate and go back and think about the numbers and go back and read it. And that's going to take a lot of back and forth reading and rereading. And hopefully, as your skill with this improves over time, that's one thing that you might end up doing less of. As you get a better feel for it, it makes more sense. You feel more confident with what you're doing. That's something you may not do as many times. But you may have to do it a lot, because notice how no three of these problems are the same. Again, the first one was talking about the distance between a point and a point on a parabola. The second was talking about air going into a sphere, and the third one was talking about water going into a cylindrical tank. You're not going to be able to memorize problems and memorize a recipe. I'm trying to give you general principles to follow so that you're able to parse, process, make sense of, and eventually ace related rates. Here's the second general principle. And the second one, you may have already noticed, you might have to write a couple of different formulas or rules or equations before you're able to make sense of what's going on. So it may take a bit of a winnowing process to say, okay, this makes sense because this, and you're going back to the text. So this is just like writing an English essay. You are finding evidence to support your position of, this is the equation I want to use. The third thing, this is the skill we just practiced to start class. Differentiating your equation with respect to time. Now, what I typically find is this is when I start being able to make sense of the situation. When I feel like I've got an equation and I differentiate with respect to time, For me, I have an easier time of matching up what's going on with the math that I need to do. It may be different for you, and that's perfectly fine. You got to find what's going to work well for you. The fourth general principle is you're going to need to determine the quantities. What do I mean by determining the quantities? Well, the best example I can share with you was previously, I just drew a green arrow pointing to it, where we took time to figure out dHdt is the height of the water. The change in the height of the water, excuse me. So you want to actually go through and look at your formula and say, okay, this is in my formula, what else do I need? Once you've got all that taken care of, you can start solving. Now, related rates when it comes to calculus is not particularly challenging. The only calculus ideas that we're talking about is the idea of differentiating with respect to time and interpreting what the quantities mean. This is one reason why we spent so much time towards the beginning of the class and reinforced periodically later on. These ideas of interpreting, when is it happening, what's happening, how is it changing, what's going on. It's to prepare us not just for this, but overall to have an understanding of what calculus means in a real context. It's not just about symbol pushing. It's not just about doing the power rule on x to the 7/5 power. That's not what calculus is just about. Calculus is primarily used to do real things like what we're talking about here. So the calculus is really just these two principles, 3 and 4. Most of, in my opinion, the hardest stuff to do here is the other math. Really, the solving is not the hard part typically. It's reading and rereading. It's determining a rule that works. And all of that is in preparation for then engaging in the calculus. So one of the really important things I hope you talked about was the different units here. And you talked about what the different numbers mean, the 3 and the 1, the D and the H. And one thing that the discussion questions emphasized that I don't emphasize as much is this idea of drawing a picture. So I dislike a few of the things that they did. And we'll talk more about that in a bit. But what I'm going to look at with you here is not meant to be largely different from your discussions. So I'm not real interested in the correct answers. So let me kind of lay out for you how my thinking went. So I got a vertical pole, and I chose to literally think of a pole like this. All right. And then after I got my pole on there, I thought about how there's an ant, and the ant starts right here at the bottom of the pole, and then it does ant things and moves this way. You can all see that moving on your screen share, I hope. So that's what the ant's doing, right? So really close to the start time, the ant is really close to the bottom of the pole, and then as time goes on, it gets further and further away. So to represent that, I drew in a horizontal side. Now this horizontal side, of course, is different distances because it depends on how far the ant has walked, how much time has passed. So if the ant is right here, that horizontal side would stop right there. Okay, okay, so that's kind of what's going on. But we can't represent all of those at the same time. That's why we just do the one side. And then the other thing that's talked about is the distance from the top of the pole to the ant, which looks something like that. Right, that's the distance from the top of the pole to the ant. I think that was H, right? They called it H. And this was D. Something like that, right? So I looked at this and I had a few thoughts. My first thought was, that's a right angle. Now notice how nowhere in the text it says this is a right angle. The reason why I assumed that this was a right angle is because I said, you know what, vertical poles are perpendicular to the ground, right? Vertical poles are perpendicular to the ground. That's what makes sense. So it doesn't say that in the problem, but I thought about how that was the case. So I looked at this, and these were the two things I was thinking about when I was thinking about modeling this, like making an equation or formula. I was thinking about the Pythagorean theorem. And the reason why I was thinking about the Pythagorean theorem is because we're looking at a right triangle and we're talking about the sides. And then the other thing I was thinking about was something like this. I was thinking about writing sine of theta, theta being this angle up here, equals d divided by h. And I discarded that. I said, that's not going to be it. And the reason why I said it's not going to be it is because we're talking about three sides. So because I was talking about three sides, I used the Pythagorean theorem. To say this was the case. And then I took the derivative with respect to time. So I'm just going to call pole little p. All right? That's going to be little p. So the derivative of pole squared is 2p dp dt. The derivative of capital D squared is 2d times dd dt. And the derivative of capital H is 2h times dh dt. And this is where I like to go in and I like to think carefully about what kind of information my formula contains compared to the information that the text contains. And what I like to do is think about it in words. And because this is the first time we're doing one of these together, I'm going to have you write about it in words. So I'm not saying every time you do one of these, you're going to want to write everything out in detail, but I am saying, especially for your notes to be helpful to you, you should. And especially when you're starting out, you should. So what's P? That's the length of the pole, right? Okay. How about capital D? What's capital D? Well, that's going to be how far, or the distance, from the ant to the bottom of the pole. Okay, how about capital H? Well, looking at the picturing, or the picture, or thinking about my picturing, what's capital H, or looking at the text? How far, or the distance, from the ant to the top of the pole. So this is all part of that reasoning process, of the self-checking process of making sure you know what the quantities mean, when they happen, what their units are, all of that stuff. So what are the units here? Well, P is the length of the pole. Looks like it's measured, everything's in feet, right? So these are all going to be feet. So that's 3 feet. I don't know what D is, but it's in feet. I don't know what H is, but that's in feet. Make sense so far? So all we're doing right now is we're just trying to picture what's going on, because each one of these is going to be unique. And I cannot possibly take the time with you to go through every single related rates problem that has ever been created. And secondly, we're not going to even anticipate every other related rates problem that's been created. All we can have are these general ideas, these ways of making sense of a very complicated and confusing situation. Okay? All right. So I've got 3 more variables in my equation. What are the other variables in the equation? Well, I've got dp dt, and I'm going to abbreviate rate of change, ROC again. I don't encourage you to do this on assessments, but I'm trying to fit things into a certain amount of space. dp dt is the rate of change of the pole's length. dd dt that's the change of the distance between the ant and the bottom of the pole. Which means we got one more variable. Don't worry about the stuff in purple. We'll come back to that. That's a placeholder to remind me to come back to it. So don't worry about writing anything in purple right now. Just the stuff in red. Actually, I can get rid of that. I don't need that anymore. Talking to myself, sorry. Last but not least, we need dH dt. So what's dH dt? So think about it before I'm about to write it down. What do you think dH dt is? Now, something you may have noticed in my writing here, I've tried to write all of these a little bit different. Not because I think of them differently personally, like I think of them all the same way, but what I'm just trying to capture for you in the writing is that the thinking might be a little bit different here, the work might be a little bit different here, the wording, the situation, and we got to try to stay as flexible as possible. We don't want to try to make this into a recipe, because if we make this into a recipe, we're going to be very, very confused. Okay, so this is in feet per minute, hour, I can't remember. It's probably hours, hour, nope, it's minute. It's a fast ant. All right, these are all in feet per minute. Okay, and then we know one of these is 1. Which one of those? That's the ant in the bottom of the pole. That's a 1. All right. Now, there's something really, really important that is not spelled out in the problem or in any of the reasoning you've done, but I still think you need to do. Anytime you're thinking about one of these, You want to be thinking to yourself, is this a positive number? Is this a negative number? Is this a zero number? Which one makes sense? So this is not spelled out in any way in the problem, usually. What we have to do is we have to end up determining that. So all of these distances, seems like those are all going to be positive numbers, right? Yeah, those are all going to be positive numbers. The ant's not going to walk -5. That doesn't make sense. Okay. These rates are a little bit, well, they're the same here. That's not true. But it's the same kind of consideration. It's the consideration of, okay, is this a thing that is positive, negative, or zero? These are both positive. The reason why these are both positive is because both of these are distances that are increasing, which I determined from the context of the problem. Definitely as the ant gets further away from the bottom of the pole, the distance from the ant to the bottom of the pole is larger. Well, similarly, the ant is going to be further from the top of the pole. Because think about what we've got. We've got this right triangle here, and we're talking about making this side get larger. And if this side is getting larger, the angle across from it is also getting larger, which means the side connecting those two has to be getting larger as well. The one I'm going to have you think about over the break is this one. dp/dt, the rate of change of the pole's length. Is that positive? Is that negative? Or is that zero? So that's what I want you to think about. The pole is 3 feet tall. The ant is crawling at a rate of 1 foot per minute. The ant is crawling away from the base of the pole. That means the distance between the ant and the base of the pole is getting larger. The distance from the ant and the top of the pole, which was h, is also getting larger. So what is the value of the rate of change in the scenario, including units? So we're really only given one. And that is d/dt, the distance between the ant and the base of the pole. How tall is the pole? We know that that's 3 feet. How do you know that this diagram can be represented with a diagram of a right triangle? So that was based on two things. That was, again, we're thinking that a vertical pole is perpendicular with the ground. We're thinking that we have the three sides of the triangle, one of them being the pole, the other two being the distance from the ant to the top and bottom of the pole. Before we go on to the next one, this is where I would like to talk about the question I asked you before you went on break. And that was about dp/dt. Y'all remember dp/dt, yeah? Okay, I asked you to think about that. I asked you to think about the sign. So I asked you to think about, is that positive? Is that negative? Or is that zero? All right. And you decided that this is zero. Why did you decide that was zero? It wasn't decided willy-nilly. It was decided because the pole does not change length. The pole is always 3 feet long. All right, so zipping ahead here, looking at number 4, which diagram makes sense? The pole is this, that's D, that's H. Which equation and I really don't like either A or C, but C is the closest to what we're looking for. We're going to use the Pythagorean theorem and then differentiate that. Okay, so moving on to numero 6 on the next page of the handout. It says, at a certain time, the ant is 4 feet away from the base of the pole. What is h at that time? And I'd like to mention to you that we have 2 equations we could think about solving for h. So we have the Pythagorean theorem equation, and we have the differentiated, the differential equation. Which one is going to make sense? Well, we're going to solve for h. All right, so you already know that this is 3. And then right here, we're told that this is 4. So we're going to use that first equation because we already know 2 of the values. That means we can solve for the 3rd value. Number 7 is a little bit more confusing. It says find D and H 2 minutes after the time mentioned in question 6. So what does it mean to be 2 minutes after the time mentioned? Well, let's think about it. 2 minutes after the time mentioned in number 6. How long is the pole going to be? Pole is still going to be 3 feet. How far is the ant from the base of the pole? That's going to be different this time. So we have the 4 feet, but we're adding on 2 feet. Why are we adding on 2 feet? We're adding on 2 feet because this is moving 1 foot per minute, but a positive 1 foot per minute because that distance is getting larger. So that's 6. And we're not going to, but you would then solve that for h and you choose the positive square root. Well, I guess I can. 36 and 9 is 45. So we are going to close the book on the ant situation. And the takeaways I want you to have are not specific takeaways of memorizing the ant situation or doing anything like that. Instead, what I want you thinking about is how all of the pieces fit together. And we're going to keep building towards the idea of doing related rates more independently. So I would like you to draw your attention to the next situation, what's described as scenario 2, and I know you can read, but to make it feel like we're more connected, I'm going to read to you also, because you'll be reading and rereading, and hearing it once won't hurt anything for certain. So an oil spill in the shape of a circle is expanding on the surface of a pond. The radius of the oil spill is R, measured in centimeters. Pretty small oil spill on this pond, right? If we're measuring in centimeters, I think. And the area of the oil spill is capital A, measured in square centimeters. Suppose that at a certain time, the area of the spill is 30 square centimeters and the radius of the spill is increasing at 0.2 centimeters per second. I'm not going to ask you to label the diagram. Here's what I'm going to ask you to do. I'm going to ask you to do three things. First one is I want you to choose a formula. And whether you think your formula is right or wrong, once you've made your final choice, I want you to differentiate that formula with respect to t. And then I want you to, in some fashion, identify or describe the quantities. What do I mean by the quantities? I mean the variables. So we're going to take a few minutes to do that. I will be pausing the recording here while you work on that. So this was meant to be an experience more, or to have it feel more like what doing one of these problems is like. Often you get a verbal description. Sometimes you'll get a picture to go with it. But the main thing is you need to engage in some type of mental picturing process, some process whereby you make sense of this problem. It's going to involve reading and rereading. It's going to involve coming up with formulas, equations, or models. It's going to involve differentiating with respect to time, and it's going to involve making sense of what the different quantities are. Those are the core elements of any related rates problem, no matter how complicated it is, no matter how familiar it is. So, what were you thinking about formula-wise? You were thinking this maybe? Area of a circle. Okay, why does it make sense to say area of a circle? Well, because it says shape of a circle, surface of a pond. If we put those things together, we think about area of a circle. And then when you differentiate this with respect to time, you get dA dt. Pi is a constant, so it's pi times 2r dr dt, which I'm going to write in this fashion. Okay, so looking at my differential equation, the equation I differentiated with respect to time, I have dA dt in it, I have r in it, I have dr dt in it, and I want to make sure I know what all of those things mean. I'd also like to think about their values, and I'd like to think about the sign of those values. That's this whole picturing process, interpreting process, connecting the math we're doing to the situation we're in. All right, so dA dt, how could we describe that? You could call it the change in area. You could call it the change in area over time. R, that's the radius of the spill. dr dt, you could call that the change in the radius of the spill over time. You could call it the rate of change of the radius of the spill. All of these are correct ways of phrasing the interpretation. Okay, so how about these values here? So dA dt is not provided to us, correct? Not provided to us, okay? So that's an unknown amount of stuff. But we can infer from the situation that dA dt is going to be positive. How do I know it's going to be positive? Because in the text it says expanding. All right. How about the radius? Well, we read through and we don't know the radius either. It's not specified for us, is it? Okay, but what do we know? If we're measuring radii, those ought to be positive. And then finally, dr dt, we're actually given this one. This is a 0.2 centimeters per second, and that's getting larger. So I know that that's positive. So if you have something like this on your analysis here, you did a mighty fine job of analyzing what's going on. So if you take a look at the equation that you came up with, you might notice that in this equation, it's not really going to be possible to solve for dAdt right now because we don't know dAdt, and we don't know r. The only thing we know is drdt, just like we couldn't solve for r in this equation because we don't know dAdt. So we don't have quite enough information here to make sense of everything we need to make sense of. Okay? All right. So here's what's going to happen, and you're going to work on this, well, for a couple minutes on your own and then with your teams for a few minutes. You're going to work on the backside 9 and 10, and don't look at anything I've got here, that'll be disappearing. 9, 10, 11, and 12. So that's on the next page. I want you to work on those. Some of those should go quickly, some of them should go slowly. And I will get you arranged. So you worked with your teams and you hopefully came up with something similar to the following information to some extent. So we know that the correct equation is going to be the area of a circle equation. If we differentiate that equation, we have two differential or derivative or statements of change. We have drdt, which is the change in radius of the spill in centimeters per second. We have dAdt, which is the change in area of the spill. That one's going to be in square centimeters per second. Now, what I'd really like to do is spend some time talking about 11 and 12. So if you can find your highest level of focus for that, that would be super. So number 11 says, what is R at the certain time given in the scenario? And we're not told what R is, right? R, as presented, is unknown. But R is gettable. What I mean by that is, if you take a look at this equation right here that we came up with before we differentiated with respect to time, pi r squared, I know that A is 30 square centimeters. That means I can solve that equation for R by dividing both sides by pi and then taking the positive square root. So I know what the radius is. It's whatever the square root of 30 divided by pi is. So make sure whatever decimal you have is equivalent to that and is accurate to 3 decimal places. And then that helps us answer number 12. So number 12 says, if the rate of change of R continues to be 0.2 centimeters per second, what is A after 3 more seconds? So you might be tempted to do something really wrong here. You might be tempted to say that A equals 30 plus 0.6, and the 0.6 is the 3 seconds times the 0.2 centimeters per second. You might have been tempted to do that, but that's not right. That is flat out wrong. Few reasons. One is because the 0.2 is the change in radius, not the change in area. So you can't just add a change in radius to a change in area. That's not how that works. Those are different quantities of change. We spelled it out up here in variable land. We said drdt and dAdt are different. Area is different from drdt. You can't combine those. Those are different things. You can't just add one to the other, even if you've said it will be 0.6 centimeters larger. So what you need to do is make sure you're adding like terms together. Specifically, we need to add area to area. So we want to add 30 units of area to however much more area we have after 6 seconds. Does that work? Type it out. While you're typing it out, let me break down what we've got here. So we've got the radius when the area is 30 plus the 0.6, which is after 3 seconds. If we do that, we have the original radius plus the radius 3 seconds later. That should be our new area total. Yes? Yes. Okay. So with that in mind, what I'd like you to do, and I'm going to send you back to your teams, is work on number 13. So I'll give you about the same amount of time to digest what we looked at, as well as figure out the new stuff. All right. So 13 adds in a new piece of information. New piece of information is right here. The oil spill is expanding so that its area is increasing at a constant rate of 0.4, and we're now told that the area is 50. What is R at that time? R is going to be done the same way as number 12 did it, where we have the equation A equals pi R squared. We know that A is 50. We can solve for R by dividing both sides by pi and then taking the positive square root of both sides. Now to figure out A and R 10 seconds later, we've got a little bit more straightforward, I guess that's the phrase I'll use, way of doing this. So we have an increase for area. So if we add 10 seconds of the increase of area to the area of 50, and if we add 10 seconds to the increase of radius, we're assuming the radius is still increasing at 0.2 centimeters per minute or second or whatever it was, seconds. Then we're able to answer that. If we don't have that, then we'd have to do something a little bit different. While you're making your final thoughts on this situation, I want to start talking about what we're going to do next. Okay, we're not going to do the next page in the handout. We're skipping that. Instead, we're going to be looking at the ant situation again. And for the ant situation again, you've got a little bit different information this time. I want you to look at 1, 2, 4, and 5. So the only thing you're not going to look at is the table, number 3. And we're going to start doing that in a couple minutes here after we take ourselves a nice deserved break. Okay, so taking a quick look. Number 1 was confusing to me for a few reasons. First of all, they have D with a lowercase h instead of an uppercase h. Sounds a little bit annoying. The other thing I didn't like was it didn't say from the bottom of the pole, it just said from the pole, and there's 2 distances. Now they did clarify to say 1 foot per minute, which was why I was pretty confident saying dt. But otherwise, a little bit confusing. So we can now replace D with 4. And then on the back side, letter A is the first choice. The reason why it's the first choice is because if we look at the equation we came up with, which had the 2h dh dt equals the 2d dd dt plus the 2p dp dt, dp dt is 0 because the length of the pole doesn't change. And if you look at this equation and you're solving for dh dt, That's not a bad piece of algebra to have to solve for, right? 2 times 5 equals 2 times 4 times 1. That's pretty trivial. So the hard part is getting to here. Once you get to here, about the only thing you want to do is just be careful, make sure you're following good equation solving practices and remembering your units. All right. So next thing we're going to look at is going to be a solo endeavor, and then I will go over it. I would like you to do for number 1 on part 2 solving, I want you to do the sketch, and then I can't remember which part it is. So don't look at the other stuff on here. I think, yeah. I want you to sketch and do the formula. And the sketch doesn't have to be a sketch. I want you to picture. And remember, I'm using a very expansive view of what it means to picture. So when I say picture, I don't mean you literally have to draw out the picture, but what you want to do is take this long paragraph of text and start translating it into a useful way that you can actually do math on. So if that involves lots of writing, that's okay. If that involves sketching a picture and writing, that's okay. If that involves just writing some ideas down, that's okay. But just make sure that you take time to do this, because when you look back on this to study, you may not remember exactly what you did. The main idea with picturing is not drawing the picture, it's about picturing or creating a mental picture or creating some understanding of yourself, or taking all of these words. 2 cars leave Central Square. The first car drives north at 35 miles per hour, MPH. Its distance to Central Square is A. Here, A is actually a function of time. The second car drives east at 50 miles per hour, and its distance from Central Square B. Here, B is also a function of time. The distance between 2 cars is D. At a certain time, A equals 20, B equals 40, both measured in miles. You need to take that and put it into some scheme that makes sense to you. That's what the act of picturing is. The act of picturing is not necessarily the things that I've done. So yes, I've sketched a picture for you to look at. And yes, I've used words to talk about it, but you don't have to do it in that fashion. You just have to do it in a way that makes sense to you, to the point where you can actually start accessing some additional math. Like, for example, we know we have a right triangle because one car is traveling north and the other car is traveling east. North and east meet at a right angle. That right angle has to be where Central Square is. And because we're talking about the 3 sides of a right triangle, it makes sense to consider the Pythagorean theorem, whose derivative with respect to t is shown here in part C. I think you always want to pause at this point in time and think about what these things are. So I've got an A, B, D, dA dt, dB dt, dd dt. You always want to consciously think about what you're doing. You don't want to be going on autopilot and saying, this is just like that other thing. That's going to be bad for you. It's going to cause you to miss stuff. So A, that's the distance from the first car to Central Square. B is the distance from the second car to Central Square. D is the distance between the 2 cars, dA dt. I know that that's positive because car A is driving away from Central Square. Likewise, dB dt, dd dt. Well, if 2 sides of a triangle are getting larger, what's the third side going to have to get? It's going to have to get larger as well, isn't it? Yeah. So those are all positive. dABT or dA dt, dB dt, dd dt, those are all in miles per hour. A, B, and D, those are all in miles. All right, so I've done all of my analysis. I'm ready to start doing stuff. So what kind of stuff do we do with all this information we collected? Well, we try to answer a question about it, like this one. Are the 2 cars getting closer or farther away from each other at the certain time? How fast is the distance between them changing at that time? Well, we've already answered this first part. We know d dt, the distance between the cars, is positive. It's because the other two sides are getting larger. So the third side has to be getting larger as well. Okay, so how would we actually solve for that? How fast is the distance between them changing? Well, the distance between them changing is d dt. So that's what we need to solve for. So what we need to go back to is make sure we know what A is. We know what A is. Make sure we know what dAdt is. We know what that is. Make sure we know what dBdt or B is. We know what that is. Make sure we know what dBdt is. All four of those are in that ginormous paragraph. A is 20, B is 40, dAdt is positive 35, dBdt is positive 50. The rates are in miles per hour, the distance are in miles. The only thing we don't know is D, but we can solve for D using the Pythagorean theorem. Because we know A and B, if we square those values, 20 and 40, add them together, take the square root, we know what D is. So take a look at the equation we actually need to solve. The only algebra I'm doing from here is I'm combining like terms and dividing by whatever that product is. That's it. All of the hard work, all of the calculus, all of the reasoning, everything takes us to what is typically an equation that is not that difficult to solve. Not always, but often. So when you're looking at these related rates questions that you're going to be practicing, the things I want you thinking about are those general ideas. No two related rate questions are necessarily the same. If you're memorizing problems or processes, you're making a mistake. You want to be thinking about the general ideas. You want to be thinking about how you have to read and reread, how you have to interpret, how you have to connect those ideas to formulas, how you have to differentiate the formula with respect to time, how you have to go back and make sure all of the quantities match and make sense. And you know, like which ones are positives, which ones are negatives, and which ones are zeros. Those are the things you want to be thinking about when you do these related rates questions. There's not going to be a single necessarily concise way to say, do this every time. Each one's going to be a little bit different.